Welcome to this explainer. Today, we're taking those abstract, kind of intimidating calculus formulas and turning them into real physical objects. We're going to translate those dry symbols on your page into tangible shapes, stuff like growing areas and expanding volumes. It's going to be a lot of fun. Let me kick things off with a question. Why do math students waste so much time just blindly memorizing derivative formulas? We often treat them like magic spells that we just have to accept. But what if, instead of rote memorization, we just understood the real-world geometry of those small increments? On one hand, you've got the traditional headache of memorizing abstract algebraic symbols. On the other hand, you have geometric meaning, and there's this incredible aha moment when you stop seeing just x's and y's and start actually visualizing how shapes grow in physical space. That geometric intuition is exactly what we're going to focus on today. All right, let's dive right in. We are going to totally redefine the abstract term x squared. Instead of just thinking of it as x times x, I want you to physically picture it as the actual area of a square with a side length of x. Seriously, let your brain make that fundamental paradigm shift for a second. So, what happens when we grow this shape? Let's walk through the geometry of that growth step by step. If we increase our side x by a tiny little step, which we'll call dx, we visually add three distinct new pieces of area to our square. We get two thin rectangles on the edges, each with an area of x times dx, and then one totally tiny corner square with an area of dx squared. And this brilliantly illustrates the core secret of derivatives, understanding the derivative as simply a rate of change. Let's say our tiny step, dx, is 0.01. That means that little corner square, dx squared, is 0.0001. It becomes infinitely small. It's so microscopic that when we focus on the intuitive feel of small increments without getting bogged down in complex algebra, we can actually just mathematically ignore it. The bottom line is this. If we drop that microscopic dx squared corner, we're left with just those two thin rectangles. Their combined area is 2x times dx, divide by that step size, dx, and you're left with exactly 2x. Boom! This proves that simple geometry perfectly explains the algebraic derivative of x squared. No crazy math required. Now let's scale this whole discovery up to 3D. We're going to look at x cubed not as a formula, but as the actual physical volume of a growing cube that has a side length of x. If we grow our cube by that exact same tiny step dx, we're adding new volume, right? But where does the bulk of that new volume actually go? It's concentrated in three main square faces, added to the outside. The volume of those three faces is 3 times x squared times dx. And just like with our 2D square, we have extra little pieces, the edges and that one tiny corner cube, but they involve dx squared and dx cubed. They are absolutely negligible, so we can safely toss them out. By ignoring those tiny pieces, we get 3x squared. Do you see what's happening here? Our intuitive visual of shapes growing using simple examples smoothly formalizes into the standard power rule. The exponent jumps to the front, representing the number of growing faces, and the power itself drops by 1, representing the dimension of those faces. All visually, without any complex algebra. Section 1, the 1 over x rectangle constraint. Let's transition to a new concept. We're going to introduce a dynamic physical constraint to help us perfectly understand negative derivatives. Picture a 2D puddle of water shaped like a rectangle, but there's a strict rule here. Its area is locked in at exactly equal to 1. So if the width of this puddle is x, the height must literally be 1 over x to keep that area at a constant 1. Now, here is a physical thought experiment for you. Let's visualize. How will the height change if the width increases? If we bump up the width x by a tiny step, dx, what physically has to happen to the height to ensure the total area stays perfectly at 1? Well, to compensate for the new area we just gained by pushing out the side, the rectangle physically has to shrink in height. The area lost from the top has to perfectly equal the area gained on the side. This intuitive visualization shows exactly why the derivative of 1 over x is negative. To keep the area constant, the height literally drops. Section 2. Hacking the quotient rule. Let's pivot to a notorious pain point for calculus students, the messy quotient rule. I promised you a clever shortcut, right? On the left, you've got this terrifying massive fraction formula you'll find in textbooks. But on the right, you have the much simpler, far more elegant product rule. What if I told you that you really only need the one on the right? Let's walk through this trick step by step. We are going to derive the quotient rule using the product of a function and its inverse. Instead of dividing f of x by g of x, just rewrite it. Write it out as f of x times g of x to the power of -1. Now just apply the product rule to this new expression. Take the derivative of the first times the second plus the first times the derivative of the second, using a little chain rule for that negative exponent. Boom, you just turned a nasty division problem into a totally manageable multiplication problem.
This brilliantly illustrates our whole philosophy today, perfectly summed up by this quote from secant. I frankly always forget the quotient rule, and I just rederive it from the product rule. See, understanding the underlying structure is always better than blind memorization.
Section 3, the final challenge, the square root. We've explored areas, volumes, and even hacked the quotient rule together. So here is my final tantalizing geometric puzzle to wrap up this explainer. What is the precise geometric meaning of the derivative of the square root of x? How can you take the visual growth rules we talked about today, apply them to the square root, and explain geometrically why its derivative is tied to the slope of a tangent line? Take everything we've learned, sketch out the shapes, and see if you can solve this entirely with geometry. Thanks for exploring this with me, and never stop visualizing the math.